Okay, so today we're working on chapter 7, which is the evolutionary game theory. And so here, behavior is going to be like a strategy and fitness is going to be like a payoff. So let's get started and take a look. In the previous section, we looked at game theory from a perspective of players simultaneously reasoning about what to do in a game. Evolutionary game theory says, hey, nobody's really overtly reasoning. This is just, it's kind of happening. It's a competition between two species or an interaction between two organisms. They're not overtly reasoning, selecting one strategy to play versus another strategy to play. So we can be interested in the forms of behavior that have the ability to persist within the population. Evolutionary biology is based on the idea that an organism's genes largely determine its observable characteristics and hence its fitness in a given environment. And a lot of the behaviors involve the interaction of multiple organisms within a population. So how do they interact and what roles do they play? The success of any of these organisms, of course, depends on how its behavior interacts with others. So in terms of a fitness being a result of interaction, we can look at an example with beetles. Now, this one's not going to be perfect from a biological standpoint. This is, after all, a computer science textbook, but it illustrates some of the main ideas with this concept. A beetle's fitness is based on its ability to find food and to use it effectively. Now imagine that we have a mutation that allows the beetle to become bigger. So there's a mutation that makes for a large beetle. Is that good or bad? Well, there's some bad to it because if you have more body weight or you're a larger body, then you need to have more food to maintain that bigger body. But it can be good because you can crowd out the smaller beetles in order to get more food to maintain that larger body. So what happens when the big beetles and the little beetles interact? Well, when beetles of the same size compete, they get equal shares of the food. So when a small beetle competes with a small beetle, they each get 5. When large competes with the large, they each get 3. And the 3 versus the 5 is reflective of the fact that the larger beetle needs more food in order to maintain its size, so it doesn't get as much of a reward for sharing the food. When a large beetle competes with a small beetle, the large beetle gets the majority of the food. There's also something different about this game, and compared with the game theory that we saw in the last presentation, and that's that beetles don't get to choose their size. Hey, I'd like to be big today, or small beetle today. We need to think about how these strategies operate over larger timescales or over larger scales within a population. So this brings us to evolutionarily stable strategies. A genetically determined strategy that tends to persist once it's prevalent in a population is a genetic or an evolutionarily stable strategy. In the beetle example, each beetle is repeatedly paired off with competition of other beetles for food over the course of its lifetime. Sometimes you may get a small beetle to compete against. Sometimes you may get a large beetle to compete against. A beetle's overall fitness will be equal to the average fitness it experiences from each of these different encounters over the course of its lifetime. And this overall fitness determines its reproductive success. In this setting, we say that a given strategy is evolutionarily stable if, when the whole population is using that strategy, any small group of invaders using a different strategy will eventually die off over multiple generations. They won't be successful in breaking into the population. So some formal definitions of fitness. The fitness of an organism in the population is the expected payoff it receives from an interaction with a random member of the population. Invades, we say that the strategy T invades a strategy S at level X for some small positive number X. If an fraction X is using T and 1 minus X is using the strategy S. So say it's some small number, like say 5%, then that would be an invasion. A strategy S is evolutionarily stable if there's a small positive number y, such that when any other strategy T invades S at any level X is less than y, the fitness of an organism plane S is strictly greater than the fitness of an organization plane T. So let's see if either small or large is evolutionarily stable for the beetles in our examples. And we can start with small. So suppose for some small x, a portion 1 minus x uses small and x uses large. Here x corresponds to the large beetles, they're the invaders. The expected payoff for small is 5 times 1 minus x. Basically they'll encounter small beetles 1 minus x percent of the time, and they get a payoff of 5. But if they encounter that large beetle, they only get 1, so they get plus 1x. So that's 5 minus 4x. The expected payoff for large, the invaders, is 8, because when they encounter the small beetles, they get 8 plus 3 times x in case they encounter one of their large brethren, which it makes 8 minus 5x. And in the graph, you can see 8 minus 5x pretty much dominates the 5 minus 4x for any x between 0 and 1, which is the probability. So for small x, large exceeds small, so small is not evolutionarily stable. Well, let's look at large and see if that is. Is large evolutionarily stable? So imagine that the large beetles form the major population. We have an invading force of small beetles. For the expected payoff for small here is 1 minus x, because they get 1 bit of food when they encounter the large beetles, which are 1 minus x percent of the population, plus 5 times x when they encounter a small beetle. So that gives a total of 1 minus 4x. The expected payoff for large is 3 times 1 minus x, which is when they encounter another of their large brethren, plus 8 times x when they encounter one of the small beetles that's invaded. So they have a total of 3 plus 5x, or 5x plus 3. When we plot those, we see 5x plus 3 is bigger in all cases than 4x plus 1. So large is actually evolutionarily stable in this condition. So, a few small beetles will do very badly, losing almost every competition for food. As a result, the population of large beetles resists the invasion of the small beetles. In the previous example, the large beetles will crowd out the smaller beetles because they do well as an invading force. The text also talks about how game theoretic reasoning can provide qualitative insight into different forms of biological interactions. And they give some examples, trees growing large or small as an analogy to the beetles examples, soybean plants that share a pot of soil, and they can either be explorers where they grow out their roots long, which expends energy, or conserve energy by having shorter roots. And they talk about the interaction of 2 viruses, Phe6 and Phe2, and which one is works well in that competition. Now here's where I'm going to deviate a little bit from the text explanation, since our knowledge about plants is continuously evolving, and there's been a lot of recent work on the subject. Susan Semard has a number of different TED Talks on how plants actually communicate and cooperate, and the book here is Finding the Mother Tree. She looks at the world of trees and illuminates the fascinating and vital truths that trees are not simply sources of timber or pulp, but are a complicated interdependent circle of life. That forests are social cooperative creatures connected through underground networks by which trees communicate their own vitality and vulnerabilities with communal lives that are not different from our own. Trees, living side by side for hundreds of years, have evolved. How they learn and adapt their behaviors, they can recognize their neighbors, compete and cooperate with one another, is very similar to civil societies. And at the center of it all, she has a concept of a mother tree, the mysterious, powerful forces that connect and sustain the others that surround them. They've also done studies on mushrooms and shown that mushrooms know up to 50 words that they can communicate with one another. They talk, that is with quotes, using electrical impulses that spike when fungi come in contact with either food sources or potential dangers. So we're learning a lot about how plants communicate with one another, and this is actually a worthy explanation if you're, or worthy area of exploration if you're into the biological aspects of things. We'll also need to look at symmetric games, and this will help us with the concept of evolutionarily stable. So symmetric games are games where the roles of the two players are interchangeable. The payoff matrix for a completely general two-player, two-strategy game that's symmetric is shown here on the right. If both choose S, they get A. If both choose T, they get D. And C and B are interchangeable if one chooses S and one chooses T. In this two-player, two-strategy symmetric game, S is evolutionarily stable precisely when either A is greater than C, or A is equal to C, and B is greater than D. So this leads us to evolutionary equilibrium. If the strategy S is evolutionarily stable, then SS is a Nash equilibrium. However, we can have games where SS is a Nash equilibrium, but S is not evolutionarily stable. In the version of stag hunt that you see here, hunting stag is a Nash equilibrium, but it's actually not evolutionarily stable here, since the payoff for hunting the hare is the penalty for hunting the hare is not significantly lower than hunting the stag. In fact, if one chooses to hunt stag and the other chooses to hunt hare, the hare hunter will get the same reward as they would for hunting the stag. That 4-4 is Nash equilibrium, but it's not evolutionarily stable. Over time, it will tend to die out if it's an invader. So what if no strategy is evolutionarily stable, such as in the hawk-dove game? This game has two pure Nash equilibrium of dove-hawk and hawk-dove, but neither one of those is evolutionarily stable. Basically, if you're always a hawk, you might end up with in fights, and if you're always a dove, you may be shorted on food. So we can generalize this to allow for some mixed strategies in the game. It's likely that each individual is hardwired to play a particular mixed strategy, and they can choose randomly among certain options with certain probabilities. So, sometimes I can be a hawk, sometimes I can be a dove. A mixed strategy has probability P that an organism plays S, say that's a hawk, and plays T with probability 1 minus P. In the general symmetric game, P is an evolutionarily stable mixed strategy if there's a small positive number Y, such that when any other mixed strategy Q invades P at level X less than Y, the fitness of an organism playing P is greater than the fitness of an organism playing Q. And basically, P needs to be selected so that it makes the other player indifferent to either of the two pure strategies, such as our matching pennies game. And for the hawk-dove game, we can show that P is equal to 1/3 for dove is evolutionarily stable. And, in terms of doves, and in terms of, like the virus example they give where one only exists to benefit the other, there is, sometimes an undesirable fitness lowering role in a population of organisms. But if some organisms don't choose to play that role, then everyone suffers. So sometimes an organism actually needs to be selfless for the good of the entire population, which is something interesting to think about. And that's it. Thank you so much for watching.